All right, then welcome everyone in the lecture hall, usual 100 students, and welcome everyone online if you're watching the video. So it's again my turn after being away from the videos for how many weeks? 1, 2, 3, 3.5. Okay, so I'm back for the second part of lecture 8, and I think I'm also doing lecture 9. Let's see. All right, so Andrew came here as a student of Macintosh and talked about Macintosh theorem in the last lecture. And so today I'm going to pick up on Macintosh theorem. I'm going to explain a little bit consequences that we didn't write down last time, also to get you back on track. And then we're going to use Macintosh theorem to prove a rather surprising result about fractional powers of M-accretive operators. Okay, so last time on this show, Quadratic Estimates versus Functional Calculus, Andrew showed you that in virtue of Macintosh theorem, two things are equivalent. So there was a notion of quadratic estimates, which was the requirement that for some, and then equivalently all, h0 infinity functions, you could control this quadratic integral where you use auxiliary function f and the functional calculus of L, and L, as always in this lecture, is an injective sectorial operator in a Hilbert space H. And if you can control this quadratic integral from above and below by just the norm of U, and that was sort of reminding us on basic Littlewood-Paley inequalities or quadratic estimates that we proved using Fourier transform in the fourth lecture. If this works for the operator, this is equivalent to saying that the operator has a bounded H-infinity calculus, and somehow because you're only evaluating this auxiliary function along real parameters, the angle of the sector on which this f is defined is not appearing anywhere here, and this is reflecting in the fact that also the notion of bounded H-infinity calculus is independent of the angle larger than the angle of sectoriality of phi of L, of course. Okay, and that was one surprising thing besides the characterization of H-infinity calculus through something that heavily smells like Fourier analysis in the first place. Okay, and so one important corollary that we should write down is the following. So imagine that L is an injective M-accretive operator. Okay, then you know from lecture 7 for Neumann's inequality that this operator has a bounded H-infinity calculus of angle larger than pi over 2. But now, in view of this Macintosh result and the independence of the angle, you can write down that L has a bounded H-infinity calculus of any angle larger than the angle of sectoriality. In other words, the H-infinity angle and the angle of sectoriality, they are the same. Okay, and the proof, as I just said, is a two-step procedure. You first use von Neumann's inequality 7.12, and then you combine it with Macintosh theorem 8.11. Okay, and so you see that the L infinity, so thinking of operators like our divergence form operators that are associated with sectorial bounded elliptic sesquilinear forms. In this case, the angle of sectoriality is less than pi over 2. Okay, and so we get a bounded H-infinity functional calculus where we can plug in the operator into functions that are defined on sectors that are just ever so slightly larger than the angle of sectoriality. Okay, so the image you should have in mind is that here's a complex plane, okay, and then there's a sector opening of angle phi of L with a spectrum of this operator somehow sitting inside. Okay, so this is the spectrum of the operator in case the angle of sectoriality is less than pi over 2. Okay, so this is the spectrum. Oh, by the way, nobody ever wanted to put advertisement here, so I'm going to do that myself. So this spectrum is sponsored by my own bike racing team. You can look up the blog and learn about the cyclist Moritz. Okay, that is just a short side trip. The important thing I want to tell you is, now imagine that I have a holomorphic function f that is living on a slightly larger sector. I'm going to use some other color for that. Okay, so imagine this angle here is an angle phi between angle of sectoriality and pi over 2. Then I can take h infinity functions on that sector, and there's a h infinity calculus for holomorphic functions on that sector that gives you bounded algebra homomorphism and so on and so forth. But the way that you get that is by this two-step procedure. Okay, and so in the first step, in 7.12, you actually take holomorphic functions that are defined on much larger sectors, namely sectors that open up with an angle larger than pi over 2, because the crucial thing to get anything that looks like h infinity calculus was to say that f of L, by this magic formula using symmetry on the imaginary axis, could be computed by integrating along the imaginary axis something. Okay? That was the starting point of all. And then von Neumann's inequality worked, and you got the h infinity calculus of large angle. And then in the second step, 8.11, you change the angle. 8.4, sorry. 8.4, and then this is also 8.4. Change the angle. Okay? And so it turns out then, at the end, that you have inbounded h infinity functional calculus for functions which are not even defined along the crucial path of integration in von Neumann's inequality. Okay, so this is kind of a remarkable thing in this two-step procedure. Okay, you stop me if you have any questions, as always. All right, so just a minor remark. You know, you have this equivalence, so both of these statements in the equivalence, they come with a certain amount of implicit constants. Here it's, when you fix the angle, it's most notably the bound for the h infinity calculus, and here it's the implicit constants hidden in these quadratic estimates. And from time to time, it's good to know what these things actually depend on and how they depend on each other. And you can track that. I mean, we didn't do it. We just wrote twiddle and so on the board, but it's not difficult to track it and gives it actually nice and natural dependence. Okay, so let me just say that Macintosh's theorem can be made quantitative. Okay, and this is an exercise. If you're solving the exercise, I think the best way to solve it is actually to first try to guess what the constants, if you go from here or back, will actually depend on, and then you're going to justify your guess in this exercise by going through the proof. All right, so that's it for Macintosh's result. And so I want to show you one application of Macintosh's result that brings us back to the fourth lecture, where we were able to determine fractional powers of the Laplacian. And we had like fractional Sobolev spaces, and then we had explicit formula for the L2 norm of fractional powers of the Laplacian applied to a function. Formula that did not use any sort of multiplication operator on the Fourier side, but like double integrals, plain exact formulas. Okay, and so I want to do something at the end of this lecture for elliptic operators with coefficients, which is going to forbid every single tool that we used in lecture 4. And I want to convince you that the things that we did over the last 4 lectures are powerful enough to just do that without Fourier analysis. Okay, so this section is called Cato's theorem on subcritical fractional powers. Okay, I'm going to explain all the terminology for you. Cato is a mathematician, you know, from lecture 6. Fractional powers, you know. Subcritical is going to become clear at the end. Okay, so the setup for this part is like in lecture 2. So there's this Gelfand triple, there's V, a Hilbert space, continuously and densely embedded into our standing Hilbert space H, and then there's the dual V prime, and so this is as in lecture 2. Okay, and so the starting point of this story, just to give you a bit context before stating mathematical theorems, is that Cato at the beginning of the 1960s, he studied something what calls a non-autonomous evolution equation. So it's an equation of the following type. There's a time derivative, so something evolves as time passes, and then there's coefficients L of t, U of t, and that should be equal to f of t for t in some interval. Okay, and then there should be initial condition for u at time 0. The interesting thing in this equation, okay, called non-autonomous evolution equation, is that these coefficients here, L of t, they're actually not coefficients in the sense that you know from ODEs, but they're operators. Okay, so u is a function valued in h, and L of t is a maximal accretive operator associated with a sesquilinear form that also depends on t, but is defined on the same form domain V. Right, so for every t, there's a sesquilinear form that has some properties, bounded elliptic accretive, for example. And then each of these sesquilinear forms on the same Hilbert space V can generate an operator in H, as you've seen in lecture 2. And then these L of t operators, they are part of this non-autonomous evolution equation. And it's non-autonomous because this L of t depends on t. Now, there is, if I just throw that equation on the table for you, and I'm going to ask you, say me one issue that I'm certainly going to have when I start digging into theory of this equation. What would you say? What can be annoying? Imagining, if you want to make sense of that, U of t should be in the domain of L of t. Now, the domain of L of t, it can change in the most dramatic way, even though all the sesquilinear forms are defined on the same Hilbert space V. Just think back to our elliptic operators. Then we had these elliptic operators with the most horrible regularity theory, namely the intersection of the domain with H2 is trivial. And then other nice operators like Laplacian, the domain is exactly H2. Okay? So this L of t, the domain of L of t, is prone to severe changes when you switch from one sesquilinear form to another one. And so that's the issue, right? So issue, the domain of L of t varies a lot. Okay, and so of course, Kato knew that, and his way out, I mean, there is no way out if you want to include elliptic operators in divergence form. You cannot say that this domain is not going to change, but what you can do is the following. So Kato's way out, he wanted to have the following. The domain not of L of t itself, but the domain of L of t to some power 1 over m, where m is some natural number, that should be independent of t. Okay, and that is what he calls, or what we would call, a stability property of that thing. Okay, so on the level of m is equal to 1, there is no hope. But maybe for larger values of m, there is hope. Okay. And actually, he was able to prove that if he has this stability property, then in a suitable sense, for given initial datum for u, he's able to produce a unique solution in some appropriate sense in some class, using the stability property. And then, even more remarkable is, when you look at that, you say, okay, that's fine, but is this going to be true? Why should it? Well, there's some indication that something like this could be true, because when you think back to lecture 6, if I assume that all these sesquilinear forms, they are actually symmetric, then the operators they generate, they are self-adjoint, and then we have the fact that the square root of these self-adjoint operators has domain equal to v, and v is not changing. So for self-adjoint operators, m is equal to 2 would work. And in the general situation, Kato was able to prove, under the assumptions I'm going to put down, that m is equal to 2, he didn't know, but m is equal to 3, 4, and so on and so forth, he knows. And that's the theorem for today. Okay, so 8.12, the following theorem. I assume that A1, A2 on V, they are two bounded elliptic sectorial sesquilinear forms. Okay, you know that small a is always a sesquilinear form in my writing. I'm going to suppress that when I write it on the board. And these guys, they generate L1, L2, the associated operators in H. Okay, so two sesquilinear forms, they fit into the framework where they generate an M-accretive operator, and these guys I'm going to call L1, L2. Okay, and then I'm going to take a parameter alpha, which is going to be between 0 and 1/2. My goal, or the goal of the theorem, is to say that the domain of these of the fractional powers of these operators L1, L2, they don't change under suitable assumptions on the sesquilinear forms. So what assumption do we need? The assumption is as follows. Suppose that I can control the real part of the quadratic forms, in the sense that the real part of A2 of u is bounded by constant times the real part of A1 of u, and that works for every u in the form domain. If I can compare the real parts of the quadratic form, This implies that the domain of L1 to the alpha is contained in the domain of L2 to the alpha. And in addition, we have an estimate, namely L2 to the alpha of u is controlled by L1 to the alpha of u whenever u is in the domain of L1 to the alpha. All right? The inclusion that I want to deduce from the assumption goes the right way, because this ordering of the quadratic forms somehow says it's more difficult for an element to do something good for A1, because A1 is larger. Okay, so if I manage to do something good for the more complicated operator, then I'm also going to do something good for the easier operator. So if I'm in the domain of L1 to the alpha, I'm also in the domain of L2 to the alpha, and the new information is controlled by the old one. Right? So the theorem goes the right way round. Before jumping into the proof, let's write out two consequences. They're probably more interesting than the theorem itself in view of the stability property. So the first one is, if instead of this one-sided controllability of the sesquilinear form A2 by A1, I make the assumption that actually these guys can be compared in both directions. So if I make a two-sided assumption on the real parts of the quadratic form, then this implies indeed that the domain of L2 to the alpha is the same as the domain of L1 to the alpha, simply because I can apply the theorem in both ways. And so the two-sided comparability of quadratic forms gives equality of the fractional power domains, plus it gives the two-sided estimates for the fractional powers. So you can compare the L2 norms or the H norms of the fractional powers. When does that happen? Well, if I'm given any sesquilinear form A1, this assumption is always true if A2 is the adjoint form, because for the adjoint form you have the same real part. Okay, so in particular, if I take A2 to be the adjoint form of A1, then I get that the domain of L1 to the alpha is the same as the domain of L1 star to the alpha. And if I want, by properties of adjoint calculus, I could also put the star out so that the domain of L1 to the alpha and its adjoint, they're also the same. Okay, and that's always true. If the operator is self-adjoint, this second information doesn't tell you anything. Okay. Good. Do you have questions on what I'm trying to prove? Please. Yeah, because question is, why was Cato led to consider fractional powers? Because he knew that in cases that he wanted to do, he couldn't make sure that the domain is not changing as t changes. And so he needed some anchor point in his thing, and then he switched to fractional powers. You could think of having the stability on the fractional power scale as something like having stability on domains on a lower regularity, if you actually think of PDEs. That's a good question. Other questions? All right, so as a little warm-up, I I want to show you a lemma. And the lemma is going to be the way in which on operator level I'm going to use this assumption 8.5 on the quadratic forms. Okay, so lemma is as follows. Suppose A1, A2 on V, they are bounded sesquilinear forms. If they're bounded sesquilinear forms in this setting, then I can at least construct the associated operators in V prime or in H. And also suppose that A2 is sectorial. Okay, and suppose that 8.5 holds. Okay. So this inequality on the quadratic forms implies the following. Whenever I take V in the domain of the operator and I take Z in the domain of the other operator, then I can produce a following estimate. I test W against L2 of Z, and I claim I can control it by the product of 4 terms. Not just 2. I mean, two terms you could guess I could just do Cauchy-Schwarz, but this is not what I want to do. I want to do something that produces more terms than Cauchy-Schwarz, because I want to use every single information in the game. If I would just use Cauchy-Schwarz, I would use the fact that Z is in the domain of L2, but I would treat W just as any element from the Hilbert space. Right? But I want to use also the information that W is in the domain of L1, and so the claim is I can do the following. I get all 4 norms, L1, L2, Z. Okay, and then you can guess the homogeneity. This guy is like linear in V and in Z, so I should put square roots everywhere. Well, that's the lemma. And we're only going to use 8.5 in the proof of the theorem through the use of this lemma. And the lemma is funny in the sense that you introduce all these terms that you don't actually see at the beginning. So how do you prove that? Well, it starts like this. So W and Z are fixed, of course. I write out this sesquilinear inner product. And because I'm taking real parts, I could also flip the order if I like that. Okay, and I like flipping the order because if I read L2Z inner product against W, I recall the definition of my operator L2. It's exactly the same thing as having A2 at Z, comma W, absolute value. It's the definition of L2 as the operator representing the form through the use of the inner product on the Hilbert space H. All right, now A2 is sectorial, so I can use Cauchy-Schwarz inequality for sectorial forms. This was exercise 2.1. It's like Schwarz's inequality, but for non-symmetric things if they are sectorial. And this Cauchy-Schwarz inequality tells you that I can take the real part of the quadratic form of the two things, and I want to do it that way around. It doesn't matter because it's just a product of numbers. All right, that's Cauchy-Schwarz for sectorial forms. I know you did the exercises, so you're not worried about that. And now at this point, I have quadratic forms, and I can use 8.5, the assumption. And of course, what I want to introduce is more of L1, so I should just, at the expense of yet another implicit constant, I can turn this A2 into A1 using 8.5. That's all of the magic, because now, what is this, for example? This term, A1 of W. Well, this is A1 of W with itself, So this is L1 of W against W. And in the same way, this thing here, this is L2 of Z against Z. Okay? Well, now you just estimate the real part of this by absolute value, and then you use Cauchy-Schwarz on this. And so it gives you L1 norm power 1/2, W norm power 1/2, this term power 1/2, this term power 1/2. So that's all. Proof accomplished. Questions? No? All right, so we're going to use this lemma at a very specific point. I'm going to make it more dramatic for you by making a mistake, and then the whole proof looks like screwed up, and then the lemma will save us. But until we're there, we need to do all the preliminary steps of the proof. All right. Proof of Theorem 8.12. Okay, I make minor simplifications. I assume that L1 and L2 are injective operators for this lecture. And I recall that by 6.7, one of our lemmas, this implies that also the adjoints are injective, because these guys are, in particular, sectorial operators. Okay, in the general case, let me see, be more careful. Well, that would be kind of unfair, isn't it? So we make it slightly fairer, and I say, you'll be more careful, and we send it to the exercises. Okay? So exercise, I think, 8.4. It's a nice one. Going through the proof and checking where I actually used injectivity makes you understand the proof even better, and then you also generalize the statement. All right, and then throughout everything that is going to happen in this proof, U will be an element of the domain of L1 to the alpha, and then V is going to be a domain element in the domain of the adjoint fractional power. So V is going to be in L2 star to the alpha. Okay. So these things we keep in mind, and then now we keep going. Let me do one step, then we make a break, and then I do the other steps for you. So step 1. Step 1 is the following. I claim that the following, I call it a bilinear estimate. The bilinear estimate, the following one, suffices. The bilinear estimate I want to do is I want to test U against L2 star to the alpha applied to V, and I want to control that by L1 to the alpha of U times V. Okay. I mean, it's not bilinear, and also there's absolute values, but it's somehow reminding you that actually we want to prove domain inclusion. So it's just norm of something is less than norm of something, but we reduce it to something that has two variables and behaves linear or antilinear with respect to these variables. Okay, and I claim that this is enough to complete the proof. So let us see why. So, color. Suppose I have the blue estimate. Okay. Suppose I have the blue estimate. What does it tell me? Well, I can look at the following functional. V is being mapped to U L2 star to the alpha V. This is some antilinear thing, and it is defined on the domain of this operator. Right? Well, that I can always do. But now, if I suppose that I have this blue estimate, then this is a functional antilinear defined on the domain of this operator. But if I bound the functional, then with respect to V, I don't have to use the fact that I'm in this domain. I just bound it by the H norm of V. In other words, this is a functional that is bounded with respect to the topology on the Hilbert space H. It's just not everywhere defined, but the domain of this operator, by properties of fractional powers that you've seen, is dense. So this is a densely defined antilinear functional on H. Okay, so it has an extension which is a bounded antilinear functional on H by density. You can extend it like that. Is that step clear? That's the... it's an extension. The extension is a functional on H, so it's an element of H prime, or it's a functional on H. It's the same thing. Okay, so that's the key point, because now I can use Riesz representation. Riesz representation gives me some element V in the Hilbert space, such that I can write this guy as W, V, so it's an element W in the Hilbert space, and that works for all V in the domain of L2 to the alpha, L2 star to the alpha. Right? Because this functional is now going to be represented by this element W. Okay, and I also know how large the norm of W is going to be, because W is exactly the operator norm of that functional, or its extension to be precise, and the operator norm is no larger than the constant setting here. So W in norm is going to be less than L1 to the alpha U. Right, so you have that. So what does that mean, what you're having there? This means that the tuple UW is contained in a specific operator. And the specific operator, this is reminding us of the definition of the adjoint of the operator sitting here. So it means UW is contained in the adjoint of the fractional power of the adjoint. This is precisely what it's saying. Just forget what this operator is, call it T, and then this means that UW is an element of T star. Sweet. But now we have these computation rules for fractional for adjoints and fractional powers. So the star can be interchanged with a fractional power exponent alpha, but once the star is interchanged, then there's the clash of these two stars, and L2 star star is L2, because L2 is a sectorial operator, so it's closed, densely defined. And so this is just the same as L2 to the alpha. Well, if UW is in L2 to the alpha, this means that U belongs to the domain of L2 to the alpha, and that L2 to the alpha of U is precisely this guy W, And W is bounded in norm by L1 alpha of U. And so I proved everything I'm claiming. Right? So that would give the claim. Okay, so we make a break at this point, and we're going to see how to prove the bilinear estimate after the break. Let me just do a short 5 minutes break so that I don't go overtime today. And let me remind everyone watching this video that the evaluation of the internet seminar on Moodle has opened. So please, it would be wonderful for us to have as many of these evaluations filled out by you. So if you have, just do a short break yourself, refresh your mind and do the evaluation for us, and we would thank you a lot for that. Okay, and now for us is break, it's blackboard cleaning time, and then we go on. Okay guys, then let's go on. I should say, this sort of trick I used in step 1, put it in your toolkit of standard tricks. Right, so I proved that, actually in the end, I proved that U is in the domain of L2 alpha by proving that it's in the domain of the adjoint, and then being in the domain of the adjoint, I sort of rewrote as a variational thing using the adjoint operator. Because, as everyone knows, it's always hard to prove that something belongs to the domain of something. So somehow it's always difficult. Okay, so step 2. So from now on, we just worried about this bilinear estimate, and the left-hand side of this estimate I'm going to call the bilinear term from now on. Okay, and step 2 is about a reproducing formula for the bilinear term. Okay, so for the inner product of U and L2 star to the alpha of V. And the way I'm going to derive that formula is by using the following auxiliary function. Phi, just a function mapping positive real numbers to complex numbers, and it's going to be of such type that when the parameter is 0, then I'm going to reproduce the bilinear term, and I have good control on its derivative. And so what I just do here is you take this bilinear term, look sharply on it above, and then I'm going to regularize both sides using resolvents. So I'm going to put 1 plus t to the L1. I put a resolvent of L1 in front of the U, and I'm going to put a resolvent of L2 star on the term on the right. Okay, this is a nice function. I can do that. Psi of t when t goes to 0 by this all-purpose proposition for sectorial operators. These resolvents, when the parameter t goes to 0, we think always of them as being an approximation of the identity. And so they converge strongly to the identity. So when t goes to 0, I'm going to get back the bilinear term. And when t goes to infinity, I'm using the fact that I'm working with injective operators. So range is everything, and we know that this approximation of the identity, when you shoot the parameter on the wrong way, so you send it to infinity, they tend to 0 strongly. And so this function, psi of t, also goes to 0. Here I'm using injectivity for the first time. I'm going to use it 3 more times. I'm not going to tell you every time, because then I would spoil the exercise. Okay, so I have a function phi that represents the thing I want to estimate. At 0, it vanishes at infinity. So I can use fundamental theorem of calculus, and I can write this term as the integral over the derivative of this function psi. So before I should do that, I should check that the phi is differentiable and I compute its derivative. Now you know that the resolvents, these things, they are analytic functions of t. So either you use like the product rule on this inner product, or you develop both things into power series and you collect terms. Either way will show you that this function phi is differentiable and you can compute its derivative. And so the derivative is, if I do it product rule style, I have to differentiate this guy, so it gives me a minus. Then it's a L1 that pops to the front. Then the resolvent power increases by 1, and the other term is fixed. And then I play the same game on the other term. Well, it's exactly the same thing that happens, except that I get a different operator to the front, and I have to increase the resolvent power by 1, so it gives me minus 2, and that gives me L2 star of V. All right, so thus bounding the bilinear term, I write out the bilinear term by the fundamental theorem of calculus, like that, and then I bring norms inside. Then absolute value of psi prime is going to be sum of absolute value of two terms. I use triangle inequality, so I can bound this whole expression by the sum of two terms. I'm going to call 1 and 2. And I'm keeping book of what 1 and 2 is. So 1 is the integral from 0 to infinity of exactly that thing. So it's L1, 1 plus t L1 to the minus 2 of u, 1 plus t L2 star minus 1 L2 star alpha of v. And 2 is going to be integral from 0 to infinity over absolute value of that thing. Just copying. Good for you that you have printed out the lecture notes. And then there's dt's missing and there's parentheses missing. Okay, so this is dt, and the other one is this one, dt. Right? It's just a triangle inequality. And so what do we have to do? The goal is to prove that both of these terms are controlled in the way that I want it for the bilinear estimate. So I should have L1 to the alpha of u, and I should have v. That's the goal. And now I just have to do that. Okay, so how are we going to do that? Step 3. Step 3 is about winning against term 1. How do we win against this term? Let me write out the term again. So it's an integral from 0 to infinity. And then there's some brackets. There's a resolvent, t L1 to the minus 1. Then there's u. There's also some L1 I leave out deliberately at this point. And then there's a resolvent, 1 plus t L2 star. To the resolvent here was minus 2, sorry. And then there's a resolvent, this guy, minus 1, and then there's v. Okay, then there's some other stuff, and there's a dt. Okay, now I'm gonna play a little around on how I write the term that you still see here. On the right-hand side, I do something rather easy. I just switch this fractional power over here, which is okay by functional calculus rules because the v is in the domain of that operator. So that's actually the harder term to write. This operator is bounded. So it's absolutely safe to write L2 star to the alpha to the front. And then I want to make it look like quadratic estimates. So this L2 star is still missing its t. So I'm going to put a t here, and then I need to divide by t to the alpha. Then I sort of massage the second part of the term, and it's still all correct that I wrote. Now I'm going to look at the first term. For this first term, I still have stuff acting on u, but I want to have L1 to the alpha of u. So I'm using rules for fractional powers. I split this L1 as L1 to the alpha and L1 to the 1 minus alpha, which is completely okay by rules for fractional powers. And then I use functional calculus rules to throw this L1 to the alpha on the other side of the resolvent, which is okay because u is in that domain. And if I do it like that, then I'm going to stick with L1 to the 1 minus alpha. Then this operation is okay. Now I want to get homogeneity into game, so I want to put a t over here, but the t wasn't there, so I have to compensate and put t to the 1 minus alpha down there. And so I did nothing else but changing a little bit the things in terms of functional calculus. And now this here, well, let me use a beautiful color for that. This thing here, this is f of t L1, where f is some h infinity 0 function on every sector. Why? Because you have a decay power 2 at infinity, and you have decay in 0 of rate 1 minus alpha. And that thing over here, that is some g of t L2 star. And g is also in h0 infinity. G of z would be z to the alpha times 1 plus z to the minus 1. Well, alpha is between 0 and 1, so that's fine. And over there, it's t to the minus 1 minus alpha t to alpha. This gives me just t. So this is the integral dt over t, and I have two guys that look exactly like quadratic estimates. And that's going to do the job for us. Because now I use Cauchy-Schwarz. Cauchy-Schwarz gives me integral from 0 to infinity, f of TL1 applied to L1 to the alpha u, squared dt over t, power 1/2. And likewise, integral from 0 to infinity, g of TL2 star of v squared dt over t, power 1/2. And now look at that. This is quadratic estimates for L1 acting on this Hilbert space element, and this is quadratic estimates for L2 star acting on this Hilbert space element. Well, L1 and L2 star is associated to the adjoint form A2 star, which is also bounded elliptic accretive. These two guys, they are M-accretive operators, so they satisfy quadratic estimates. So I can apply quadratic estimates, and I bound the whole thing by L1 to the alpha u times norm in v. And then I win against term 1. That's it. Questions? It's pretty cool. I like it, at least. I should say at this point, what I'm doing here is not the original proof that Cato had in mind, because, quadratic estimates came way after the 60s in this context, so it was science fiction at this point, maybe. So it's not the original proof. It's a proof that I learned from Andrea Carbonaro and Oliver Dragicevic. Okay? It's a paper of theirs I read. It's a beautiful paper, and it had this beautiful proof that we just adapted a little bit to the setting of the internet seminar. All right, so step 4. I want to win against 2. So what's the issue? Have a look at 2. Do you see why it could be difficult to win against 2? I claim that 2 is much harder than 1. Look at what happens to L1. L1 is just sitting in this sole resolvent. But if I want to use functional calculus and H0 infinity functions with L1, there should be some additional power of L1 sitting somewhere. And also in the final estimate, sorry, there was a U, there's a U missing, right? I forgot the U here. Also in the final estimate, there should be some power L1 to the alpha sitting on the U. But this power can come from nowhere. I can try to move the L2, then I get way of the star maybe, but there's no reason that ever moving L2 around would all of a sudden be L1 when it comes to the other side. It's just impossible. So at this point, I'm stuck. I cannot do the same thing again. So how can we get out of it? We use tricks that work once, they're likely to work twice. So how did I get the powers in front in the first place? Because when I started, there were no power at all. It came from differentiating the resolvent. So for the second term here, there's enough powers of L2. I'm not worried about that. But for this term, I'm just using integration by parts and fundamental theorem calculus again. So I'm going to fix t, and I'm introducing a new new auxiliary function. Patrick likes to call this variable palm tree. Okay, it's epsilon, I think, \epsilon in tech. Anyway, it's just unimportant information. What this function does is a function of the variable s, and I'm taking that term here, and I just pretend that this t was actually a variable s. So I put 1 plus s L1 to the minus 1 of u, and the other term I keep fixed. 1 plus t L2 star minus 2 L2 star to the alpha of v. All right, so that when I evaluate this function at position t, it's giving me exactly what I have. Now, when s goes to infinity, then once again by this argument that this approximation of identity at 0, when you send s to the other side at infinity goes to 0, this thing goes to 0. And once again, I can also calculate the derivative of this function. It's just the same arguments as before. So derivative of this auxiliary function is going to be minus, and then it's L1, 1 plus s L1 to the minus 2 on u, L2 star 1 plus t L2 star to the minus 2 L2 star on v. Okay, that's how you compute the derivative. Okay, so now I want to write the derivative in a slightly nicer way. So derivative of the new auxiliary function at s is going to be minus. Okay, now I'm juggling the terms around just as I did before, because I want to put a power L1 to the alpha onto u. So I'm going to write it in a way that u gets an L1 to the alpha. Okay, then the resolvent I'm keeping fixed. I'm missing a power L1 to the 1 minus alpha. So I'm putting that. It takes care of the powers of L1, but I also want homogeneity. So I put another S in here, and I'm going to compensate by putting S to the alpha minus 1 outside. And then I want to play the same kind of games on the other side. So I'm taking the L2 star, I'm leaving where it is, okay, and then I move the L2. Why is there no alpha power on it? There should be an alpha power here. Okay. I'm moving this alpha power to the front as I did before, so it's L2 to the alpha, L2 star to the alpha, 1 plus T L2 star to the minus 2 acting on V. And I want to have the thing look homogeneous, so I'm sneaking in another T, and so I have to compensate by T to the minus alpha. And then I should be in business. Let me see if this is what I want. Yeah, it looks very much like I want, because if you look sharply to this expression, you agree this thing here, this is exactly the same type of thing that we had above. So this is f of SL1. And that thing over here, this is some new auxiliary function h of t L2 star. Okay, and h of z would be z to the alpha times 1 plus z to the minus 2. That's perfectly fine. Okay, so the derivative of this auxiliary function looks a lot like things that can be used for quadratic estimates. So now we go back to this expression 2, and we write down the following. So we get that 2 is equal to integral from 0 to infinity. That's what was there all the time, the integral in t. And then it's going to be absolute value of this bracket. Now this bracket is palm tree function at position t, because I put s equal to t. Over here, I get exactly what I have there. So this function at t is the same as the integral of its derivative ranging from t to infinity, because the function vanishes at infinity. So this is this guy, prime of s, ds, dt. That I can do. Now I bring absolute values inside, as I always do, at least at the right moment. And then I get integral from 0 to infinity, integral from t to infinity. I get this sort of expression, so it's absolute value of inner product FSL1 acting on L1 to the alpha u, HT L2 star acting on V. Then there's integration in S, and there's integration in t. And I need to take care of these factors, so the minus sign goes away, of course. I write it as s over t to the alpha, and the additional -1 I'm going to put in the measure. So that it is. Now I do something that Andrew did a lot in the last lecture. I'm going to do substitution. I'm going to write S is equal to TR. So I'm substituting in the S integral, and the variable I'm introducing is going to be R. And then I need to see where my things are going. If S is T times R, and it's a substitution with respect to this H measure, then ds over S is the same as dr over R. Doesn't do anything. S over T becomes just R to the alpha. And then these other things become F of TR L1, L1 to the alpha U, H of T L2 star acting on V. I can freely change order of integration, so I'm going to do dt first, and then I'm going to do dr over R. T was always and still is running from 0 to infinity, and now just only thing that one should not do is forget that we have probably to change the bounds of integration for R. You see, so S was going all the way up to infinity starting at T. So R has to start at 1 and go all the way up to infinity, so it's integral from 1 to infinity. And that's, of course, at some point there should be a less or equal when I put the absolute values inside. You still with me? Now, the R doesn't have to do anything with T, so I can equally put it outside of the integral. All right. And now I have to estimate this monster. I'm going to clean the blackboard, and while I'm cleaning the blackboard, you're going to have a look at this inner integral in T and tell me if we can do something good with it. Okay? If we can control it in a way. Just have a look at what we did in step 3 and see if we can't do the same thing in step 4 now. So it looks like a lot of auxiliary functions all over the place. So can we directly use Cauchy-Schwarz and quadratic estimates? What do you think? Who says yes, please? Yeah. Mm-hmm. Oh, the L2 star has disappeared. I'm sorry. Yeah, the L2 star has disappeared. It's still sitting here. Thanks a lot for mentioning it. The L2 star was there all the time, and I didn't do anything with it. And I also did not take it into consideration for homogeneity. So now what do you think? F is an auxiliary function, and it's already in the right homogeneity. Now H was this function, so H, can write it down. H of Z would be Z to the alpha, 1 plus C to the minus 2. If I would put this additional power, this additional operator L2 star, into the auxiliary function, I would get Z times H. Z times H is still an H0 infinity function, because the decay at 0 is 1 plus alpha, and this is less than 2. Okay, so why not do it? Well, let's do it and see if we win. So it's tempting. I'm going to call this integral J of R. Okay, and it's tempting to do the following. To do as follows. I'm going to write J of R as the integral from 0 to infinity. I leave the first factor where it is. So this is f of TR L1 applied to L1 to the alpha U. And then the second factor, I'm moving this thing together and make a new auxiliary function. Z. So Z, the function, C times H applied to T L2 star. Z times H is still an auxiliary function. If I write it like this, then I pretended as if there was a t sitting there, because otherwise it would be wrong. So that's perfect, because it gives me immediately dt over t. Okay? And now you go for it. Auxiliary function, auxiliary function. You use quadratic estimates. You first use Cauchy-Schwarz. It gives you two quadratic integrals. Like in step, where is it? It's still up there, right? Step 3, yeah, like over there. You get the quadratic integral of this guy and of this guy. Then here you use Macintosh or quadratic estimates. You get the norm of V. So if I do the same strategy as in step 3, I get for the second quadratic integral, I get the norm of V. And for the first one, what do I get? I get a quadratic integral dt over t with the r inside, but it's with respect to Haar measure, so I can do substitution. The r doesn't change anything, so it would give me L1 to the alpha u squared. Right? Without the squares, because I use Cauchy-Schwarz. And are we happy with that? This is precisely copy-pasting what I did over there. Cauchy-Schwarz quadratic estimates, the only difficulty is I use additionally, I substitute tr as a new variable s, but dt over t is ds over s. So it works out, it gives me precisely that. Do you think that's good enough or not? Not good. Why? Yes, this is a nice estimate. It says we can control this integral, but we've thrown away all dependence of r, and this is only the red part. I still have to integrate dr over r from 1 to infinity. Well, the power here, alpha is positive, so the power of r is less than -1, and so the integral would be infinite. And so this is leading nowhere. Okay? Fuck. What do we do? Right? So we have to find a way of doing exactly what we did here, except that we also have to somehow play a trick on the Haar measure so that when we do the substitution, there's not going to be powers of r just disappearing, but we should get some decay with respect to r. Okay? So we need to do the same thing, but we need to get decay in r. And this is where I wiped out the lemma because there's not enough blackboard space. So we need decay in r to finish off the argument. And this is where this lemma is going to be helpful. Okay, as a side remark, so on the side, you remember that in this lemma it was something like vector tests against other operator acting on a vector, and this vector had to be in the domain of this operator, and this vector had to be in the domain of the other operator, so we should make sure that this vector here is in the domain of L1. Okay, I'm not going to write it here, but I'm just going to write it over here. So I claim that that thing here is an element in the domain of L1. Okay, and why is this? This is because SL1 applied to FSL1 as operators. This is the same thing as ZF on SL1, because we're in the situation for the functional calculus where the right operator is bounded. So there's equality, not just inclusion. And now this operator, f is this function. If I multiply by another power of z, I will have decay 2 minus alpha at 0. It's still an auxiliary function. So this guy here is a function in the Dunford-Rees class, so this is a bounded operator. So it's everywhere defined, and so it means that whatever I take, if I first apply f, I can still apply L1, so I'm in the domain of L1. Okay, and now we're gonna say that this is our vector W, and this is L2 upper star of Z. And so it's of the form W paired against L2 upper star of Z, where W is in the domain of L1 and Z is in the domain of L2 star. And so I can apply the lemma. This was lemma, you have to help me. Which number was it? 814. Lemma 814. Lemma 814 says that this integral j is bounded by integral from 0 to infinity, and then I get four things. I get f of TRL1 to the 1/2. I get, and I get it with a L1, sorry. Then I get just the vector. So this is L1 of W. This is, and I beginning to get sloppy here. So it's this guy acting on L1 to the alpha to the 1/2. Okay, so sorry for the confusion. So this is del W. Okay, so this is L1W. Then the next term would be just W without L1. Then the next term is L2 star of Z. So it's L2 star of H T L2 star acting on V, 1/2, and the last term is, so this is Z, and the last term is just the Z without the operator. So it's this guy. And there's a dt over t. Okay, now I want to play the quadratic estimates game yet another time. So now I want to make everything homogeneous. So if I want to write this as an auxiliary function acting on this vector, then I'm missing TR. And if this guy is fine, this is auxiliary function acting on something, this is auxiliary function acting on something. If this should be auxiliary function acting on something, I'm missing a T. So how many terms did I introduce? I introduced t to the 1/2 and t to the 1/2, so I have to compensate. And then I introduced r to the 1/2, so I have to compensate. And now runs the machinery, because this is going to be f tilde of TRL1. This is f. This is going to be h tilde of TL2 star, and this is h. So I have a product of 4 terms. I use Hölder's inequality with powers of 4 in order to turn the powers 1/2 into squares. So if I use Hölder, then it's going to give me r to the 1/2, and then integral 0 to infinity. I'm going to get f tilde TRL1 L1 to the alpha u squared dt over t power 1/4. I get the same thing without the tilde. And then I need 2 more terms. So I'm getting the same thing with the f, with the h. So it's h tilde of t L2 star of v squared dt over t, 1 over 4, and then it's the integral of just the plane h. Right, and now you see quadratic estimate, quadratic estimate, quadratic estimate, quadratic estimate. There's a r missing. We've seen that if we do tr, if we do the substitution, we can actually kill the r, and it doesn't harm the H measure. And then you apply quadratic estimates 4 times. So you get r to the minus 1/2. You get the norm of L, alpha u, power 1/2. You get it twice. And then you get quadratic estimates with v, but you get power 1/2 because there's 4th roots instead of square roots. You get it twice, and then you're happy because, okay, these collapse, so kill that, move that away, kill that, move that away, and then you have your final result for JR. And that was a miracle, because now I proved exactly the same thing as in my wrong estimate. Or, I mean, it was a correct estimate, or it's just not helpful at all. I proved exactly the same thing, but I recovered a power minus 1 over 2 in R. So now I can go back to this. So I think this one we call 8.6. And I say go back to 8.6. It says that 2 is bounded by the integral from 1 to infinity over r to the alpha minus 1/2 dr over r. And now for the one and only time in this proof, I'm not just using that alpha is between 0 and 1, but I'm actually using that alpha is smaller than 1 over 2, which is the precise condition that makes this integral convergent. Okay, so this is 1 over 1/2 minus alpha, and this is finite because alpha is between 0 and 1/2. And so we win against 2, and so we proved Cato's theorem. All right. That was tough. That was tough. Do you have questions on that? So I think it's a very good exercise, the one that we're proposing, that forces you to go through the proof again and remove all appearances of injectivity. And so we have this proof that these operators generated by sectorial bounded elliptic sesquilinear forms, they have the same fractional power domains for exponents between 0 and 1/2 if you have the comparability of the quadratic forms. Now, what could this be used for? I want to apply it to divergence form operators. So I work on R omega in Rn is open and non-empty. Now I take 2 divergence form operators. I'm going to take L to be any of our divergence form operator guys with form domain H01 omega in the Hilbert space L2 of omega. So L is any of our elliptic differential operators with Dirichlet boundary conditions on this open set. And I'm going to take this arbitrary thing as L2. And as L1, what am I going to take? There's only one choice. I want to take the best of all operators that are of this form, so I take L1 to be the negative Dirichlet Laplacian. Okay? And then I claim that I can apply Kato's result to these two operators. Because lambda times the real part of the quadratic form for the Laplacian, this is just lambda times the integral of the gradient squared. But now ellipticity tells me that this is less than real part of A2 of u. And in turn, the form associated with this A2, this was A times grad u. This is bounded by capital lambda times the integral on omega grad u squared dx. And this is just lambda times the real part of A2. In other words, of A1. Sorry, I mixed up A2 and A1. So this is A1. This is A1 is A2. A2 is the Laplace. Oh, no, it was correct. It was correct before. Oh, okay. So it says that for this bunch of operators, the assumptions of Kato's result are satisfied because these are sectorial forms and I can compare the real parts of the quadratic forms. Okay, so it says, therefore, as corollary 815, that in this situation above, if I let alpha in 0, 1, then the domain of L to the alpha is the same as the domain of the negative Dirichlet Laplacian on the same configuration in terms of geometry. So I know that no matter which operator I take, the fractional power domains of these guys, they are always independent of the coefficients if alpha is between 0 and a half. And they're just always equal to that guy. It's all the same. Now this raises two questions. First question is, how are you going to find this? If I want to know all these fractional power domains in that setting, I would have to find this one. In general, there's a formula that relates this domain. So dom of minus delta alpha 1/2 omega is related to something you can learn about if you want in the project phase, is related to complex interpolation space between two things. The idea is that this domain is, because alpha is between 0 and a half, that this domain is somewhere sitting between the ground space and the domain of the square root. Okay? So the idea is that this space here can be somehow seen as something sitting in the middle here. And the good thing about this is this one you know by lecture 6. You know that this is precisely H1, 0. So it becomes a function space problem. You have to find the interpolation space between this guy and this guy. And here I know that I can determine square root domains for self-adjoint operators. So this is one thing you can do. You can also go one step further, because if omega is all of Rn, this is the case that we treated in lecture 4 for the Laplacian. We determined the domain of the Laplacian on negative Laplacian on all of Rn. We actually defined fractional Sobolev spaces by these domains, but then we also found a formula for the norm that is not making reference to fractional powers and stuff like that. So on all of Rn, we know this thing by this double integral norm, but because we're not only getting from Cato's result that the domains are the same, but also that the operators measured in L2 are comparable, we get, as the last result for today, and this is, I think, truly remarkable, the following thing on Rn. So if I have a divergence form operator on Rn, and alpha is between 1.5, then the domain of L to the alpha is the fractional Sobolev space of order 2 alpha, and we have an explicit formula, so to say, for the norm of Lu in L2, namely this is comparable to this double integral that appeared in lecture 2, and this double integral was this guy. Okay? And so, if we're interested in determination of fractional power domains of divergence form operators on Rn, we have a result. We have extended the result from lecture 4 that was obtained by Fourier analysis through the succession of all these results from lecture 5, 6, 7, and 8 to prove that we have the same type of L2 norm object describing what it means to be in the fractional power domain of this L. And this is truly remarkable because the techniques that we had in lecture 4, they would fail at square one for any of these operators with just L infinity conversion. So the whole thing that we did sort of rebuilt in terms of this operator L, the whole Fourier machinery, and in the end we proved the same result. Why did I call it subcritical after all? I call it subcritical because this result for divergence form operators is actually just a corollary of the Cato result that works for all other types of sesquilinear forms with the respective assumptions. Now, if you want to go to alpha is equal to 1/2, then there is no way of saving Cato's result, because in the 70s, Mackintosh constructed an example of an operator where it fits into the Cato theorem, but the domain of the square root and the domain of the square root of the adjoint are not the same. And we saw that Cato's result always applies that fractional powers and fractional powers of adjoint are the same. So Cato's result can never be saved when alpha is equal to 1/2. So therefore, for Cato's result, 1/2 is the critical case. The subcritical things, they work. They always work as examples for the elliptic operators. We are going to see at the very end of this internet seminar that identification, this result continues to hold when alpha is equal to 1/2, as it does in the self-adjoint case. But in the quest of proving this result, one could say that we have gone as far as one could possibly do by using functional calculus alone. If I want to go that extra step and prove this thing here when alpha is equal to 1, then I need other tools, and it's precisely what we indicated in lecture 6. You need tools from yet another field of mathematics called real harmonic analysis, and this is what we're going to start with next week. Okay? So far, that's it for today. Thanks for listening, and see you soon.